All right, good morning, ladies and gentlemen. We are going to be continuing our discussion today about types of motion and specifically about graphs of motion. So we're going to continue today looking at graphs and specifically about the slopes of graphs and what we can learn from the slopes of graphs. Let's start with a position versus time graph. So I'm going to call this a position versus time graph. And when we have the term position versus time, all that tells us is that the position is going to be graphed on the y-axis and time will be graphed on the x-axis. So this is going to let us see the position of the object as time goes by. And if we just start the object right here, it's somewhere that's, not at the origin. Its position is already positive and away from the origin. And maybe so I have my object starting here, and maybe I have it go away from the origin, but then maybe we have it go back toward the origin. Okay, and so you can see that all during there, and then maybe I've got a flat line at the end. What would that flat part, what would that flat part tell us is happening to the object? Yeah, it's at rest, it's not moving, and that's because its position is not changing as time goes by. And so we can see that in that case, the object is just there and not moving. Here it's moving away, here it's moving back toward the origin. And those all look like they're about the same steepness. We'll talk more about the steepness. The steepness, of course, is the slope. So we'll look at that. Let's see. Let's hit Control Z and erase that. All right. So there's that. My first question is let's just draw a slope, and there it is, and there it goes. And my question is, we can see the slope, the steepness of the graph. My question is, what does the slope tell us? Now, in order to know what the slope tells us, the first thing I want to ask is, how do we calculate slope? How do we calculate slope? We've talked about this before. Okay, rise over run, or change in y divided by change in x. So I'm going to write both of those down. Rise over run. And that's also change in y divided by change in x. Now, in this case, what is on the y? What is on the y axis? What do we see on the y-axis? Yeah, the position. Um, and so what we would see for the slope is we would see the change in position. Anyone remember what the change in position is called? What did we say the change in position was called? If an object changes position, it has something that starts with a D. Yeah, displacement. Okay. And so when we say change in position, that's really the displacement. Now, what's on the x-axis? Time. So change in position or displacement as time goes by. So that could be represented as delta D divided by T. And what does delta D divided by T tell us? What do we calculate with that? Yeah, the velocity. So what we see is that the slope of a position versus time graph tells us the velocity of the object. And you guys may remember when we did our lab with the circumference and diameter of the pipes, that because of the way we graphed that, the slope actually gave us a value of pi. In this case, we can take if we make 2 points on the line, get their values and say, hey, how much does it go up? How much does it go over? And if we take those and divide that, the rise over the run, we can actually find out the average velocity of the object from here to there. Now, I said the average velocity. Why is it average and not instantaneous? Yeah, that's exactly correct. Instantaneous is at one point, would be at, if we took the slope at one point on the graph, and average is what happens when we take it over a long extended period of time. And that's what's going to be happening when we use 2 points and take the rise over run, y2 minus y1 over x2 minus x1. When we're doing that, we're calculating over an extended time, and so we're finding the average velocity. But the slope at any time is the velocity, okay? And we can actually look at how it moves and sort of get an idea of its velocity. For example, what if instead of a straight line, what if I had a curved line? What if it did something like this? Okay, and this is how it moves, but we can see it starts off with a very flat line, almost no slope at all. And so that would be a very small velocity, and then its velocity would increase. Here it would actually flatten out and be zero just for a moment, so zero velocity right about there as it changed direction, and then went back toward the origin with, we can see a moderate velocity, changes direction again as the slope flattens out and becomes zero. And then of course from this dot to this dot we see a negative slope, so that's a negative velocity, just meaning it's headed back toward the origin point. And then a very steep velocity, very steep slope, another very steep area. And so we can just look, even if it's curved, we can get an idea about how fast an object is moving by looking at its slope. So the slope of a position time graph, we all have that in our notes, that the slope of a position time graph is velocity. Thumbs up that that's in our notes. Yes, yes. All right, excellent, excellent. So we'll move on. So that was a position time graph. What about another graph like a velocity time graph? So now if it's a velocity time graph, again I'm gonna say, okay, it's moving a little bit there, flattens out, moves back this way, flattens out, and then maybe moves up some. And so we can see now, is this object ever at rest? This is tricky. Is this object ever at rest? No, it's not. What would have to be true for it to be at rest? It would actually have to contact the x-axis because the velocity would have to be zero. And so at this point, then it's at rest and it rests for a little while and then maybe takes off again. So because this is a velocity versus time graph, this graph is actually a picture of the velocity. And so until it gets down here to zero, it's not at rest. All right, so here we've got, so here our object has a changing velocity. The velocity is moving from this value up to this value. All right, what do we call a change in velocity? Any change in velocity. Yeah, that's an acceleration. And so we see that it accelerates between those two times up to that time. And then it is at a constant velocity, meaning our velocity stays at a constant value until this time. And then it accelerates again, although this time in the opposite direction, since our velocity is moving, well, actually, it's just decreasing. So it's not in the opposite direction. I misspoke. It is still moving in the positive direction because it still has a positive velocity, but the velocity is decreasing. So you just really have to be careful with velocity time graphs in terms of what you see. Let's talk real quickly, though, about what the slope of a velocity time graph would be. Okay, so the slope of a velocity time graph is again equal to delta y over delta x. What's on the y-axis this time, though? Velocity. So it's our change in velocity divided by our change in time, or just the elapsed time. And what do we call, what do we get if we divide the change in velocity by the time that went by? Yeah, we get our acceleration. That's how we calculate our acceleration. And so we see that the slope of a velocity versus time graph is the acceleration. All right. And again, we can see it has a positive acceleration, no acceleration, meaning it's constant velocity. Doesn't mean it's not moving. It means its velocity is not changing. A negative acceleration, meaning, and in this case, with a positive velocity and a negative acceleration, it's slowing down. Again, constant velocity, speeding up, slowing down, and then resting for a while before it takes off again. So just something to look at. What questions do we have about the slope of a position time graph or the slope of a velocity time graph? All right, I want to make one more point here before we finish up for this session, and that is that the slope of any graph, SL, okay, yeah, that's no good. There we go, SLOPE. The slope of any graph is delta y over delta x. And so anytime you're given any graph, you need to look at it and say, what could I calculate if I took the y-axis quantity and divided by my x-axis quantity? And throughout the course, we will be looking at different graphs and finding out what their slope tells us as we divide the y-axis quantity by the x-axis quantity. So I'll say again, anytime you have a graph, you need to look at what could I get if I divided the y-axis quantity by the x-axis quantity, and that is what your slope would tell you for that graph. All right, thanks very much, and I hope you have an excellent day.